Welcome to this lecture in the ongoing series of lectures in real analysis. Today we'll be looking at L'Hopital's rule to find limits of ratio of two functions. We'll get into that. We'll need the Cauchy's mean value theorem, which we proved a few lectures ago. And this is the statement. You can pause the video and read it. And here are two exercises. We'll be using the first one. The first one really is a very simple exercise. It looks a bit wordy, but it's a very simple exercise. But I wanted to isolate it so that it does not, when we use it, it does not look like something coming out of the blue. So that's one thing. And yeah, this is also a very nice exercise, although we won't use it today. All right. So now let us get into the statement. So what we have is we have two differentiable functions defined on an open interval. You can have variants of this statement. I will state the L'Hopital rule in one way. There are multiple L'Hopital rules, but I'll just prove this one and let you figure out the others and prove them by yourself. You can consult the internet. So we have two differentiable functions defined on an open interval, and let x0 and I be such that both f and g vanish at that point, and assume two things, that g prime, meaning the derivative of g, does not vanish anywhere on a deleted neighborhood of x0, and 2 is a limiting statement, that this limit is some real number L. It exists and it is some real number L. So it is because of the first that this even makes sense. You can talk about this limit once the first statement is given, because otherwise this denominator will cause problems. Okay. So we have these two assumptions. So these are some technical looking assumptions. So the conclusion is that then G also, so there are two things. So G also, okay, let me say G also does not vanish on a deleted neighborhood, on some deleted, anywhere on some deleted neighborhood of x0, and this limit is L. So let me say a few words about what is this theorem trying to say. So suppose you have a 0 by 0 form. Because of these two things, you have a 0 by 0 form, and you want to find this limit. So what you can do is, under some technical assumptions, you can, rather than finding this limit, you can find this limit and just report that as your answer, because the theorem says that the two limits are equal. Of course, there's something that you need to check before you can even say that. So rather than finding this limit, you can find that limit. And many a times the derivatives of functions are simpler than the functions themselves. They kind of are, somehow they are smaller. Like if you differentiate a polynomial, you get a smaller degree polynomial. So it may be easier to deal with derivatives of functions rather than the functions themselves, and that's why this theorem is very useful. Okay, but the proof is not at all difficult once we have all the pieces. So first let us show that G does not vanish anywhere on some deleted neighborhood. So to prove one, assume on the contrary that G vanishes on every, somewhere at least at one point, vanishes at least once on any deleted neighborhood of x naught. So we are just assuming on the contrary to what we want to prove, and we want to come to a contradiction. So here is some x naught, and you take some deleted neighborhood and something like that, and if it vanishes at some point, it is already vanishing here by hypothesis. G is already vanishing at x naught. So if it vanishes at some other point also, then by Rolle's theorem, the derivative of G must vanish somewhere strictly between these 2 points. So by this assumption, since on every deleted neighborhood there is at least one point where G vanishes, we see that there is a sequence of points converging to x naught where G prime vanishes. So if in every deleted neighborhood of x naught G vanishes, then in every deleted neighborhood of x naught G prime also vanishes. In fact, there is that convergent thing I said was not necessary. Basically, if you have a deleted neighborhood in which G vanishes, then in that deleted neighborhood G prime also vanishes by Rolle's theorem, because if it vanishes here, it already vanishes in x naught by hypothesis, so it will vanish somewhere strictly in between. So every deleted neighborhood where G vanishes, there G prime also vanishes, and hence by this hypothesis we must have a deleted neighborhood of x naught where G does not vanish. So one follows. So this is true, and let me not write it. I'll leave you to formally write down the details of what I just said. And now we want to prove 2. So to prove 2, what we have is we want to show that this limit exists and is equal to L. But we can write this as fx minus fx naught, because fx naught is 0, upon gx minus gx naught, because gx naught is 0, which by Cauchy's mean value theorem is equal to limit x going to x naught f prime of c of x, and I will say what I mean by c of x, where cx is a point strictly between x and x naught. So this is such a cx exists because of Cauchy's mean value theorem, which we recalled in the beginning of this lecture. And just a small point of caution. Here, when we are taking this limit, we are, when I write this x, I just mean that this x is coming from a deleted neighborhood where G does not vanish, because otherwise this will not make any sense. So I hope you understand that. Fine. So Cx is a point strictly between x and x naught, and yeah, so now we apply this exercise, and that will show you that this limit is nothing but and let me argue without going into that exercise, just verbally, what is happening. As you approach x naught, cx also approaches x naught, because cx is a point strictly between x and x naught. So if x is coming closer and closer to x naught, cx is also coming closer and closer to x naught. So in other words, limit x going to x naught cx is x naught. And now you can use that composition of limits theorem. So we already have that this limit x going to x naught f prime g prime of x, this is equal to, well, this is given in the hypothesis. And we have this another limit which we just argued is that this is equal to x naught. So now you can use the composition of limit business and show that this better be L. So that's it. That proves that this is equal to L. Okay. So it's a nice proof, but given Cauchy's mean value theorem, it is not at all difficult. Okay. So this is all that I wanted to say, and this finishes our module on derivatives and differentiation. Now in the next module we will start integration, and that's a very interesting topic. It's also very easy, completely easy. It's just notationally very heavy. Anyway, we'll get there. So as usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.